This talk is titled Lyapunov-based Economic Model Predictive Control with Taylor Series State Approximations by Keshav, Kasturi, Rangan, and Helen Durand. This talk focuses on Economic Model Predictive Control, or EMPC, which is a class of Model Predictive Controller MPC designs. MPC is an optimization-based control formulation that uses a process model for making predictions of the future state to determine optimal control actions at each measurement sampling time. When the objective function of this controller is allowed to take a general scalar form, the resulting MPC is called an EMPC. Important considerations for EMPC are its computation time and also whether it maintains closed-loop stability. For EMPC, closed-loop stability is not necessarily the same as steady-state tracking. For a formulation of EMPC known as Lyapunov-based EMPC or LEMPC, it is associated with the controller maintaining the closed-loop state in a safe operating region, reflected in the figure as the red region omega rho. The objective function, or economics, is roughly most freely optimized in a subset of the safe operating region, shown as omega rho e in the figure. This subset can be larger when there is less plant model mismatch. Generally, the mismatch is assumed to come primarily from the unmodeled dynamics, though it can also come from numerical error in approximating the solution of the process model used in the controller. Often, it is attempted to make numerical error small, as reflected in the figure on the right, where different methods of the solution approximation give approximately the same trajectory. Higher accuracy approximations of the solution of a dynamic model can increase computation time for an EMPC. This work therefore seeks to make precise connections between closed-loop stability considerations and model solution approximation in LEMPC. This essentially allows the implications of numerical error to be characterized for the LEMPC design, including how they impact the stability region subset size, and can facilitate understanding of the trade-off between computation time of the controller and potentially economics via the size of the stability region subset. The specific methodology employed in this work is to focus on a class of nonlinear systems with an analytic right-hand side and analytic solutions. Then, a truncated Taylor series approximation of the solution of the dynamic model is used in the controller. The control formulation is analyzed for closed-loop stability considerations, with the truncation error for Taylor series allowing derivation of a relationship between the approximation of the process dynamics and closed-loop stability considerations. For example, the size of a subset of the safe region of operation is explicitly related to the number of terms in the Taylor series approximation. Smaller error resulting from the model solution approximation allows a less conservative subset of the safe operating region to be used in the control law design. Larger error may lead to greater conservatism, but also may decrease computation time. We gratefully acknowledge financial support from the Air Force Office of Scientific Research.